Hi, I'm Joshua Hansen, tech lead on Atlassian's ML platform team. And with me is Geoff Sims, principal data scientist at Atlassian. Now, for the past few years, we've been working on building out Atlassian's machine learning capabilities and shipping smarter experiences for users of our products. Today, we're going to be talking about a problem that I'm sure many people have encountered, which is that machine learning is expensive. There are all kinds of costs associated with training and deploying a machine learning model. And with so many different interacting systems involved, it can often be difficult to make intelligent decisions on how to design your ML solutions in a cost-effective manner. In this talk, we'll go through a real machine learning use case that we dealt with at Atlassian, where our costs were getting out of hand. Using this as an example, we'll discuss how to quantify the underlying costs of calculating and serving machine learning features, and some techniques for choosing the most cost-effective features for a model. Now, first of all, I'll introduce the use case, which we call Smart Mentions. In this use case, we have a user picker that lists recommended users whom you might want to mention in a particular context, such as a Jira issue or a Confluence page. If we select a certain user, they'll receive a notification to draw their attention to the comment. Now, this is driven by a fairly simple logistic regression model that predicts the likelihood you'll want to mention any given user at request time based on a number of signals expressed as machine learning features. A backend service then re-ranks the users in the list as appropriate. For this use case, it's important that the features that are used to make these predictions are very up to date. For example, it may be that the right person to recommend is someone who mentioned you 5 minutes ago, and so the model needs that information reflected in its features as soon as possible. As such, we're calculating the features constantly via streaming using Tekton as our feature store. Tekton writes these features out to an AWS DynamoDB store where they can be fetched at request time at low latency. Now, with thousands of user interactions resulting in features being updated every second, a real-time system like this comes at a price. There came a point where this model was costing more to run than we were happy with, and so we started considering ways to reduce the cost without compromising the user experience. Now, to change something, you first need to be able to measure it. So the first step was to properly quantify exactly how much each feature was costing us to run. Since we have streaming feature updates, the primary driver of our costs is writes to DynamoDB. DynamoDB offers two different pricing modes, and Tekton uses the on-demand pricing mode, which means you effectively pay a fixed price for each individual write. There is some nuance to this depending on the size of your writes or factors like replication to other regions, but this gives us a straightforward means of calculating our feature cost. Now, this table shows some examples of features we performed this analysis on. Using an SQL query against our data source, we're able to easily do a count of how many event updates there are for each feature over any given time period, which roughly corresponds to Dynamo writes. By looking at historical cost data provided by AWS, you can also see the average write cost per day. You can see from the table that the number of writes varies a lot from feature to feature, and the update count corresponds with the write cost. Calculating this out gives us a fairly consistent price of $12.48 per million writes, which is about what we'd expect given we replicate these features across 6 regions. This ultimately gives us the equation: cost of features equals update count times a fraction of a cent, being the cost per write. The advantage of having this equation is that we can use it as a heuristic to estimate the cost of any potential feature, even before we define it in Tekton. Of course, there are other costs associated with using the feature, such as compute or storage, but we know from going through this exercise that in our use case at least, write cost is so dominant that they can be more or less ignored. So at this point, we understand what our features cost, and we have a few obvious courses of action to try to reduce those costs. We could try to reduce the feature cost by reducing the cost per update. And this might mean changing the way we serve the feature, or if you've built your own custom serving solution, you could optimize the way it works. In our case, we had limited control over the way features were served, so this wasn't really an option. And in general, these kinds of optimizations often involve making some difficult trade-offs that might compromise some aspect of the user experience, such as latency or reliability. Alternatively, we know that the number of updates is the main driver of costs, so we could simply reduce the number of updates, perhaps by having these features update less often. Now, this would be easy to do and would lower the cost, but it's likely going to have a negative impact on the feature's usefulness and ultimately the model's accuracy. Instead, the approach we actually took was to consider which features are providing the most value and figure out which were the most cost efficient. And I'll now hand it over to Geoff to describe this in more detail.
Thanks, Josh. So if we begin by making a basic assumption that each feature has equal cost, then the first obvious adjustment we can make is to limit the number of features used in any given model. we typically start with one feature and incrementally add more. And we monitor the accuracy as we do so. So from this perspective, it's easy to see when adding more features is giving diminishing returns in terms of accuracy, and we're able to make a very simple trade-off between cost and accuracy. In this case, we can see the accuracy stops improving after around 7 features. So by using 7 rather than 10, for example, we're effectively running at 70% cost. But of course, as we've seen from Josh, some features can be much more expensive than others. So a more cunning but equally simple method we use to observe accuracy charts for different sets of features. So usually with and without the most expensive ones. In a similar vein, we're able to quantify the difference in accuracy and make a judgment call. So in this example, there's about a 4% accuracy drop using the cheaper set of features. Now, when you start having multiple models in production, you're able to be even more strategic about which features you use in a model. In this case, we're deploying a new model into production and we're able to reuse some existing features. These are the ones highlighted here in yellow. So in this case, by forcefully reusing features we knew already existed, it effectively saved us around $15,000 a year. Now, equivalently, because these features are used twice, to a first approximation, we could say that their effective cost is halved. Of course, the more times a feature is called upon, which depends on the use case, the better value you're actually getting from it. In other words, a feature which serves 1,000 users is much less cost effective than one which serves millions of users but still costs the same. Now, in general, we typically approach this by looking at both dimensions in parallel. We observe how the accuracy changes as both features are added and as expensive features are removed. So if we look at the chart on the right, the red outlined area shows a clear step change in weekly cost from around $20 per week to $80 per week. And we can see that the corresponding accuracy changes on the left-hand chart, in this case, are minimal, which demonstrates an easy feature space that we should stick to. This can have a huge impact. Adopting these simple methods here has helped us save around $400,000 per year across just 2 models. Now, this is all made possible by both the empirical verification of cost estimates, which Josh showed earlier, as well as the detailed logging and diagnostics provided by the Tekton platform. We're happy to chat more on this topic in Slack, so please reach out if you have any questions. Thank you.